Hi, AP Calculus students. It's Miss Culver working with my tablet today for the first time in a video and to work out 3.2 example problems with you on the mean value theorem and Rolle's theorem. So hoping I do a good job for you. There's a couple little glitches in this program I have, so I'm just doing my best with it. One of these days I might find a new program, but let's take a look. This one is like problem number 42. Determine whether the MVT, the mean value theorem, can be applied to the function. Let's take a look. It is a polynomial, which means all polynomials are continuous and differentiable on a closed interval. And here's the closed interval. In the book, it's a different interval. I picked 0 to 1. If the mean value theorem can be applied, and we see that it can, then there is guaranteed to be some x on the interval from 0 to 1 where the derivative equals the average rate of change. And according to our steps, the first thing we do is find the average rate of change. So what I do first is I do f of a, and that would be f of 0. And when I put a 0 into the function, I get a 0 out. And my f of b is a 1. And when I put a 1 into the function, I get a -7 out. Is that true? Yes, it is. So now let's do f of b minus f of a. Let's do that slope formula. That's a -7 minus 0 over 1 minus 0. And so the average is a -7. Now let's go ahead. Next step is actually take the derivative of the function, which is 4x, that's an x right there, cubed, minus 8. There we go. And we are going to set that equal to the average rate of change. And let's go ahead and solve for the x where that happens. I am first going to add an 8 to both sides. There we go. I'm going to divide both sides by 4. And I get x cubed equals 1/4. And I am going to take the cube root of that. There we go. That is the cube root there. It doesn't look much like it. So x equals, see if I can do better. Oh, there we go. The cube root of 1/4. Notice that that would be a positive answer. And so it is in between 0 and 1. Let's try the next problem. Number 44, determine whether the mean value theorem can be applied to the function. Well, let's take a look. It's a rational expression. It is on a closed interval. But if you notice here, this function is not continuous at x equals 0, and 0 lies in between -1 and 2. And so we cannot apply the mean value theorem on this problem. That's a T. There we go. You may say, Ms. Culver, why don't you erase? Because when I erase, it makes a little comment section. Anyway, moving on. Number 60, when an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1500 degrees Fahrenheit, very hot. 5 hours later, the core temperature is down to 390 degrees, right? Obviously, it's heading towards that 90 degrees. Explain why there must exist a time in the interval when the temperature is decreasing at a rate of 222 degrees per hour. So this is the MVT. So first of all, notice that this is a situation where this function, you can, based on the fact that it's temperature, that you can find the rate of change at any moment, right? At any moment between 0 and 5 hours, there is a rate of change of the temperature, right? And there is a temperature. So the function is differentiable and continuous. It's also on the closed interval from 0 to 5. So it would appear based on the situation, even though we haven't been given a function, that the mean value theorem does apply. So let's do f of b minus f of a. So basically what they told us is that at time of 0, the object was 1500 degrees, right? And then at a time of 5, it was 390 degrees. So let's do our slope formula. 390 minus, that's a minus 1500 divided by 5. and that equals a negative 222 degrees of Fahrenheit per hour. So it is guaranteed somewhere on the interval from 0 to 5 that there is a point in time where the temperature is decreasing at a negative 222 degrees Fahrenheit per hour, based on the fact that that derivative would equal this rate, average rate of change over the interval. On our next problem, number 3, explain why Rolle's theorem does not apply to the function even though there exists, whoops, let's put a little s in. Can I do a little s? I cannot. There we go. A little s. Oh, maybe I need to hit that. Oh, well, there's a little s. There exists in A and B such that f of A equals f of B. So notice if you did put a 0 into the function, that it actually does, the f of B and the f of A are actually equal to each other when you put in a 0 or you put it in 2. But we want to know why Rolle's theorem doesn't apply. Well, those are all the conditions of the mean value theorem. And so we have to make sure this function is continuous and differentiable from 0 to 2. Well, when you take a look here, if you actually draw this function, we know what this looks like, right? Here's 0, 1, and 2, and I'll go back this way here. So this is an absolute value function. So it has the V shape. It has been moved to the right 1, and it is up 1, and it has been reflected. So this is actually what the function looks like in between, 0 and 2 here. Notice that the function is not differentiable. The derivative is not the same from the left and the right at the point 1, 1, which is in between 0 and 2. So this function is not differentiable. So Rolle's theorem does not apply in this case. Okay, let's go to number 6. Find 2 x-intercepts of the function, right? So those would be x's where the function is 0. Notice that would mean that f of A would equal f of B. And show that the derivative is equal to 0 at some point between the 2 x-intercepts. So this is Rolle's theorem, right? Let's take a look. This is a polynomial, so it is differentiable and continuous. It will be on the closed interval because it's asking us to find the 2 x-intercepts that make that closed interval. And we can see that the x-intercepts here are when x equals 0 and when x equals 3, right? So we do have a closed interval that we have created ourselves from 0 to 3, and the function is continuous and differentiable, right? And so somewhere it is guaranteed in between an x of 0 and 3 that the derivative is equal to 0. So let's go ahead and do that. I'm first going to write the function as x squared minus 3x. And when I take the derivative then, that would be 2x minus 3. And so we are going to set that equal to 0. And we get x equals 3 halves. Notice 3 halves is right in between 0 and 3. That's not always true, but without a doubt, we found the x that was guaranteed that there would be a derivative of 0 on this closed interval. On number 12, determine whether Rolle's theorem can be applied. Let's take a look. It can, because it is a polynomial, so it's differentiable and continuous, and it's on a closed interval. And let's see if our f of b equals f of a. So when we put in a 1, let's see, that would be 1 minus 5 is a negative 4 plus 4 is 0. And f of 4, when I put in a 4, that would be 16 minus 20 is negative 4 plus 4 is 0. Now what I want, so f of b does equal f of a. Now, by the way, f of a and f of b don't have to equal 0. They just happen to in this case, right? So they just, so they're equal to each other. They could both be 1s, both be 5s, both be negative 10s, and Rolle's theorem would apply. Okay, it just happens to be 0 in this case. If Rolle's can be applied, and it can find all the values of x equals c such that the derivative is 0. And let's take a look then. the derivative of the function would be 2x minus 5. Let's set that equal to 0. That would be x equals 5 halves. Notice that does occur in between an x of 1 and an x of 4. Last one is a little harder, right? Because simply because it is trig, right? Determine whether Rolle's theorem can be applied. Cosine of 2x, right? Cosine is a continuous differentiable function. It is on a closed interval. Let's see if f of a equals f of b. So that would be f of negative pi. When we put in a negative pi, cosine of a negative 2 pi then would be 1, right? And f of pi, right, when we put in a pi, that would be cosine of 2 pi would be a 1, obviously, because we're at the same place. So f of a does equal f of b. So there should be guaranteed that there is an x value where the derivative equals 0 between negative pi and pi or more. So let's go ahead and take the derivative, right? So the derivative would be by the chain rule, right? That's an equal sign again, right? We have an outside function of cosine. So that would be a negative sign, and we keep the inside function the same, times the derivative of the inside function is 2. And we are looking for where that equals 0. Notice I can divide both sides by a negative 2. Here we go. And we get sine of 2x equals 0. Now, this can be hard for students. We know where sine is 0, right? But where is sine of 2x equals 0? It's hard to say. So let's just call 2x theta right now. And let's first find where sine of theta equals 0. Okay, so let's see. Sine of theta is 0 at 0 and at pi, right? And that would also happen when I look here at my original period. I see that it does include negatives. So let's see, from 0 to 2 pi, right? I have that sine is 0 at pi, and at 2 pi. And let's go negative. Sine of theta is also 0 at negative pi and at negative 2 pi. So I got a little extra in there. Okay, that's where sine of theta equals 0. If I put theta in, any of these thetas in, I do get a 0 out, okay? But here's what I know. My theta is actually 2x. So let's get rid of my theta. It's actually a 2x. And to solve then for x, I'll divide everything by 2. And I just have to be sure to pick values that are in my interval of negative pi to pi. Let's see. So that would be 0 would be my first. Here we go. Pi over 2 does fall in between. There we go. This is pi. Now you may say, well, pi is on this interval, right? But it has to be continuous and differentiable on the open interval. So we don't actually include the endpoints. Only on the open interval is it differentiable, and this is the derivative from negative pi to pi. Don't worry, that's a very minor point to make. Negative pi over 2 is between negative pi and pi, and this is negative pi, which falls on an endpoint, right? And it has to be differentiable on the open interval. So these are our final answers, right? So again, to recap, for the function cosine of 2x between a closed interval of negative pi to pi, it was guaranteed, because f of a equals f of b, that the derivative was 0, hence Rolle's, you can hear the 0. Rolle's theorem, it was going to be 0, the derivative would be 0. Because derivatives are on open intervals, I found these values where the derivative is 0 on the open interval between negative pi and pi. So thanks for hanging out with me, and have a great day.